Thanks. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, we thank you that we can have your righteousness instead of our own, which is worthless, and we thank you for that. Thank you for making this world so that we can enjoy it, and I just pray that you bless this class and help us to learn the math we need to learn today, Lord. In your name I pray. Amen. Okay, so today I'm going to build a machine, and with this machine we will solve many problems. And this is the first example really of it's a couple things. I mean, the problem it solves, of course, is an important problem, and the problem is this. So here's the problem we wish to solve today. We want to solve the nth derivative of y plus, let's say, an minus 1, y to the n minus 1, let's say of x, plus da-da-da-da, plus a2 y prime prime, plus a1 y prime, plus a naught y equals to 0. So this is known as the nth order constant coefficient. Let me tell you a little bit more about that. Constant coefficient, here I'm assuming that a n minus 1 all the way on down to a2, a1, and a naught, these are real numbers. Constant coefficient, nth order, constant coefficient, homogeneous, ODE. So what I want to do is I want to build a series of results today that will allow us to solve this problem in general. All right? That's our goal. All right. That's our goal. So the way to do this is to talk about operators. What is an operator? So an operator does what? You feed it a function, right? You got some kind of operator. What comes out of the operator? Let's call the operator T. Or I'll call it L. I'll call it T. I can't make up my mind. T. So out comes T of F. What is T of F? Solution. Now you're getting ahead of the story. Not a solution necessarily. I mean, this is detached from any differential equation even. The point is an operator takes in a function and it spits out a new function. So this is what operators do. They give an operator a function, and what does it give you back? Another function. Maybe the same one, maybe a different one, right? What's an example of an operator? So some good examples, maybe, for example, t equal to d dx. This would be an operator. See, because if I give you a function, right, and then we take the derivative of that, what do we get? Another function, right? So a typical notation here will be we'll use big D for this today. In fact, for most of the course, big D. What else would be an operator? How about what's called t squared? This would be d squared dx squared, right? Also an operator. We can take the second derivative of a function, right? What else? What is another example of an operator? How about this? Here, and how do you define an operator? So what this means, right, is t squared acting on f. How's that defined to be? That's defined t of f. This is how operator works. When we square an operator, what that means is to operate 2 times. Right? So powers of operators mean successive composition of the operator with itself. But this illustrates a general principle, which is we define operators by their action on an arbitrary function. All right? That's how to define an operator. So I could do this, right? Here's another operator. T of f. How about this? I take the function, I do, say, c times f. Where c is a constant, right? Take a function, multiply it by a scalar, a new function, right? This is also an operator. Does this make sense? Another example of an operator. T of f is equal to, say, f squared plus f cubed. There's another example of an operator. You get the idea. Now, the first three of these examples, 1, 2, and 3, these are all examples of what are called linear operators. Why is that? T is a linear operator if T of C1 F plus C2, C1 F1 plus C2 F2 is equal to C1 T of F1 plus C2 T of F2. So linear operators allow us to break up linear combinations. We can pull constants out and we can break up across addition. So you guys know that's how the derivative works, right? Even the second derivative is also linear, right? If I ask you what's the second derivative of f plus g, what is it? It's f prime prime plus g prime prime, right? And you can pull constants out of second derivatives just the same. And even this c times f, if I take a scalar multiple of a function, that's also a linear transformation. Well, what's not a linear transformation, of course, is this fourth example, right? If I take t of this last one here of 2 times f, what happens? We get 2f squared plus 2f cubed, and what's that? Well, it's certainly not equal to 2 times t of f, is it, right? For arbitrary functions, certainly not. So this is a nonlinear operator. Yep.
What about number 2? Is that linear?
It is linear. Here's the proof. So t squared of c1f plus f1 plus c2 f2. Let's see how that works. So this is d of c1 f1 plus c2 f2, right? So that's equal to d of c1 df1 plus c2 df2. Then I can pull the constant out again. I get c d df1 plus c2 d df2, aka c1 t of f1 plus c2 t of f2. So, in fact, this continues to be true. If you calculate the nth derivative, right, d to the n, this is also a linear transformation. Because it's, well, there's a larger theorem here. The theorem is this. The composite of linear transformations is, well, I'm sorry, I should say linear operators. Composite of linear operators is a linear operator. Yeah.
Would that last step be c1 t squared of f1 c2 t squared?
Well, my t here was, I'm sorry, you're right. I meant to put t here like that and then say t was equal to d squared. Sorry about that.
Okay.
Although you're right, I did that over here. Ah, curses. I'm sorry. I need to make a decision about what my notation is for this example. Hopefully I have not confused you that much. Actually, let me try to confuse you more. No, just brief comment. If we have t and s linear operators, then it is in fact true that t plus s and CT and the composite, which we just write T times S, all linear operators. So if you add linear operators together, they give you linear operators. If you multiply them by a constant, linear operator. If you compose them, linear operator. And so here, when we multiply operators, this means composition of operators. All right. So this theorem is something we study, for example, in linear algebra. But here, I'm really just talking about the derivative. I mean, I'm talking about this somewhat abstractly, but primarily, I'm just looking at sums and multiples of derivatives. All right? Why am I doing that? If you go back to our original problem, what's our original problem in operator notation then? The thing we're trying to solve, this is d to the n, right? Plus a n minus 1 d to the n minus 1 plus plus a2d squared plus a1d plus a naught, all that whole big old operator there acting on y gives me 0. Okay, so I can look at this nth order constant coefficient homogeneous ODE. To study it, I need to study how do I work with operators like this, operators that are built from sums of repeated differentiation operators multiplied by constants, right? Okay, so before I get to that, I just need to do a little bit more background here. This example is kind of important. So let's see here. This will help us get a little bit more accustomed to this way of thinking. We can define T of f equals to x, well, so this is kind of obnoxious, but this is a function, right? So to define it at x, I should say that that's x times d acting on f. In other words, this is equal to x df dx. Okay. Or I could just, aka, I could say that t is equal to x times d. What I mean is that this operator, how does it work? We differentiate and we multiply by x. That's how this operator works, right? So consider that. And then also, we'll let, well, excuse me, no need for anything else. Let's look at t squared. What is t squared? So here's my question. Do you think t squared, I mean, you'd be tempted to say this, right? T squared, it's xd squared, right? So what should it be? It should be like x squared d squared, right?
Do you have to do the product rule for that?
So do you have to do the product rule for that? That is a foreboding and useful comment, because we should put a big old question mark here, because in fact, this is not true. Let me show you why that's not true. So this is lie. Or at a minimum, it's a half-truth, okay? So let's work it out. What is t squared actually? So what you said about the product rule, so good. So t squared acting on f, this would be xd, xd acting on f, right? I'm going to use some prime notation because it's helpful. So this is really x times the differentiation operator acting on what? This is what? This is x f prime, right? Now what he said is just perfect. I mean, this is a product of x times a function, right? So I have to do the product rule. When d hits it, what does that give us? It gives us, you know, dx dx times f prime plus x times f prime prime. Of course, dx dx is just 1, right? So just to, you're using like 3 different notations for derivatives here. Can you make up your mind? No, I refuse. So they're all good. So x d acting on f plus x squared d squared acting on f. And what I'm about to write is actually a definition. How do you add operators? You add them pointwise. So this is like actually xd plus x squared d squared This is a operator, and it acts on the function f. Going from here to here is just a definition. That's a definition of how we add operators. All right? You'll forgive me if I don't write all the definitions I'm using in here. If I did, you guys would get very bored. You'd rather see me calculate. I'm pretty sure. Now, you notice that this equality holds for what? For what f this holds? What was this f? It was an arbitrary function, right? So when an operator equation holds for arbitrary function, that gives us equality of operators. And so what this shows us is, in fact, that t squared is equal to x times d plus x squared d squared. Or in other words, xd quantity squared, which is t squared, is equal to xd plus x squared d squared. Excuse me. Like I said, it's a half-truth, right? That's part of it, but that's not all of it. See it? See, this is just part of it. There's also this piece. Y, product rule. Another example. Let's see here. Is x times d equal to d times x? This is as an operator equation. So maybe I should say it this way instead. T of f equals to xf. And, of course, d of f, you know what that is, f prime. So my question really, perhaps stated in a less ambiguous way, is t times d equal to d times t? So let's calculate. T d acting on f is what? This is t acting on f prime, right? Because df is f prime. What does t do? This t multiplies by x, right? So the answer here is x f prime. How about the other way around? dt acting on f.
I mean, you have to do the t first.
Right, we have to do, right? So that's d of tf, which is what? That's the derivative of x times f. Now we go back to the product rule, right? Differentiate product must do product rule. So this is f plus x times f prime. So this shows you no. In fact, no. Right? If we calculate, let's say, dt minus, good grief, dt minus td, all right, this is equal to what? Just, all right, f. So I guess I need to let this act on f, don't I? Otherwise you can't make sense of it. Now the function which spits the, what do you call the function that spits the function back out again? Like this is 1 times f, right? So it's, take the function, multiply by 1, right? Or the identity operator, if you like. So this tells me that dt minus td is equal to 1. They don't commute. In fact, this is what's called a commutator. This is the commutator of the differentiation operator with multiplication by x, which I've called t. And I've just shown that's equal to 1. Or in the usual notation, sometimes written like ddx, commutator with the multiplication by x operator is equal to 1. And this is a formula you might find in a quantum mechanics book. Although in quantum mechanics book, they usually do something like they put a little hat. They put a little hat over the x to indicate it's an operator. But you can study that more in our quantum mechanics class, right? guys should demand more. You pay a lot of money. Let's see here. Let's see here. Anyway, my point to you is simply that operators don't have to commute, right? Operators don't have to commute, do they? These don't commute. T times D is not D times D. Okay? Now, all of these cautionary tales aside, guess what? The ones we're interested in, they commute every different which way. So here's the deal. Lemma 1 is that if I have, let me get to the point here. D, I don't know, I'm not sure what's the most efficient way. I'm just going to write down a few of them. All right, guys. So say if I have D plus, let's say D plus A times D plus B, guess what? That's equal to D squared plus A plus B, D plus AB. Lemma 2. If we have A times D to the n, it's equal to D to the n times A. Right. Lemma 3. If I have a polynomial in the differentiation operator, all right? And that multiplies by d to the say n, I'll say k. Then that's equal to d to the k times the polynomial in the differentiation operator. Which one should I prove? Let me look at lemma 3. How about that? I'll show you lemma 3, okay? I'll try anyway. So what's P of D here? I'm saying P of D is something like that. It's, you know, d to the n plus, let's say b to the n minus 1, d to the n minus 1, plus da 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 da, plus b2d squared, plus b1d, plus b naught. It's this operator. So if I take this, right, P of D, polynomial in the differentiation operator, and I let it decay, multiply by dk, I act on f, what's that equal to? That's equal to P of D, right, acting on what? Acting on the kth derivative. Well, let me just say d. I'll say the kth derivative because you get a better sense of what's going on. So the kth derivative. Right? But what is that? That is d to the n on the kth derivative. I guess, I don't know. I'll make up my mind eventually here. I'll just write it that way. My apologies, guys. I can never decide a notation. For you math majors in here, I'm not giving you quite the full proof, and you'll forgive me for that. I'm trying to show enough here that everybody can make sense of it, okay? And probably, when I'm older and wiser, I'll just say this is true and not even show you details. But I'm not that wise yet, so still burden you with a few details in here. So, like, what am I doing? I'm just feeding the kth derivative of f into this operator, right? What I get b2, then I get b1, d. But how does this work, though? What happens when we say, like, d, take the derivative of the kth derivative of f? What does that give us? How do these work? I mean, this is what? This is d to the n plus k, right? And you'll forgive me if I don't write everything down. what can we do? There's a common kth derivative everywhere, right? So we could say, well, this is the same as taking the kth derivative of what? Of the nth derivative of f. I think I didn't write down. The n minus 1th derivative of f all the way on to b naught of f, right? Because it doesn't, I mean, this is the thing, differentiation, I'm taking so many derivatives, right? It doesn't matter. The basic property is, I mean, the thing that's really driving this identity is the fact that d of I plus j is equal to d of j plus I, right? In other words, I can either first differentiate j times and then differentiate I times, or I can first differentiate I times and then differentiate j times. You're like, well, duh. That's true, right? But that's has pretty dramatic consequences. It means that this kth derivative operator commutes with a polynomial in D. That's what that ends up meaning when we sort through this calculation right here, right? The next step is that this is d to the k times the polynomial in D acting on f, but f is arbitrary, right? F is arbitrary, so this proves lemma 3. Let me give you a very low-tech example of this, okay? It's in case there's still somebody who doesn't believe. How about this? Let's look at d squared plus 4d plus 3. This should be equal to what? What do these lemmas really say? They say that the polynomial, they say that polynomials in the differentiation operator obey what? They obey rules of ordinary polynomial algebra. They say that you can factor, just like normal. So if there's any justice, this should be the same operator as this. Now that we can check pretty easily, right? Here's a concrete check of that. D squared plus 4d plus 3. You let it act on a function y, let's say. That gives me y prime prime plus 4y prime plus 3 times y, right? What happens when I feed the function y to d plus 1 multiplied by d plus 3? What's that mean? That means d plus 1 acts on what? Y prime plus 3y, right? So there's two terms. There's the differentiation operator on y prime plus 3y, but there's also the multiplication by 1 operator on y prime plus 3y. And what happens? Well, we get y prime prime plus 3y prime plus y prime plus 3y, aka y prime plus 4y prime plus 3y, which you can recognize is the same thing as this, right? So what I'm trying to tell you is what I just did in example 3, it continues to be true for products of more operators, right? The interesting thing is that this is also equal to what? You know, corollary to this is that I could also write d plus b times d plus a, right? These kind of operators commute. Because I can switch a and b here, right? This just switch a plus b is b plus a, right? A times b is b times a, which gives me that. Everybody with me? All right. So I think, I hope I have done enough that what I'm about to do will make sense. Lemma 4. D minus lambda acting on e to the lambda x equals to, by the way, let us understand, for this lecture, d is always d dx. On the test, I like to say let d be d dt. See if you pay attention. Because the independent variable matters, right? If the independent variable is x, then we're looking for functions of x. If the independent variable is t, we're looking for functions of t in our answer, right? So I do usually test on that because I found it's an issue. Anyway, what is this? This is equal to 0. Okay? Now, proof. Now this proof is really complicated. Check it out. Hold on. So d minus lambda, right? E to the lambda x is what? So we take the derivative of e to the lambda x, right? And we take minus lambda e to lambda x. But what is the derivative of? Right, lambda e to the lambda x. So these guys cancel out. We get 0. You're like, but you just pulled that from the thin blue sky. Like, how do you know that? Fine. You people and your desire to see derivations. In another notation, this is the same as what? This is the same as if I plug a y. I mean, d minus lambda acting on y equals to 0 is what differential equation? This is the differential equation dy dx minus lambda y equals to 0, right? Through either separation of variables or the integrating factor technique, whatever floats your boat, you can easily derive e to the lambda x as the solution to the green differential equation. Not a big deal, right? So it's a natural guess, my lemma 4. Lemma 5. D minus lambda squared y equals to 0 has y equals to e to the lambda x. Let's say y1 equal to e to the lambda x and y2 equal to x e to the lambda x as solutions. Oh man, I buried the lead. Something important to know about a linear operator, like a very important fact about a linear operator, something I should have emphasized because it's really important to us. What does a linear operator do to 0? So let's think about it. Linear operator, 0 plus 0, what happens to it? I'm sorry, I've been using t, haven't I? T of 0 plus 0 is what? T of 0 plus t of 0, right? But it's also, if you allow me this short manga style calculation, might want to move the camera over here. T of 0. Thank you. I saw that. Let's see here. So this says what? T of 0 is? Subtract from both sides, right? T of 0 has to be 0. So linear transformation maps 0 to 0. Okay? So that's kind of important here because the proof has 2 stages, right? I mean, I guess you don't need to look at it from that lens, but maybe it's good to do that. So if I say d minus lambda squared, right, and I feed it e to the lambda x, what happens? So it's operate 2 times, right? So the first one does what? By lemma 4, we already know this is what? 0. But my point to you is we've got d minus lambda acting on 0. But this is a linear transformation. D minus lambda is a linear transformation, which means when you feed it the 0 function, guess what happens? It gives us back 0, right? I mean, of course, you could just say, well, lambda times 0 is 0, and the derivative of 0 is 0, so we get 0, and that's also true. But I want to make a point. Okay, great. So apparently, y1, check. So, right? It solves it. We plug it in. It gives us back 0. It's a solution. How about the x? So d minus lambda squared on x e to the lambda x. What happens there? We get d minus lambda. And then then d minus lambda. And if you don't mind, I'm just going to go ahead and distribute. So that's the derivative of x times e to the lambda x, right? Minus lambda times x e to the lambda x. So what happens there? Again, we know it, we love it, we don't forget about it. The product rule. So I've got the product of x and e to the lambda x. So product rule tells me that this is what? E to the lambda x plus what? X. Derivative of e to lambda x is? Lambda e to lambda x, right? And so, see what happens to the offending, or maybe not offending, but the x terms, they do what? Cancel. What are we left with? What happens when we feed e to the lambda x into d minus lambda, though? It annihilates it, right? It kills it. It sends it to 0. And there you go. That shows you that y2 is also a solution to d minus lambda squared acting on y equal to 0. Okay? Lemma 6, if we have d minus lambda, right, to the nth power acting on y equals to 0, this has solutions. y1 e to the lambda x, no surprise there. y2 equals x e to the lambda x, and so forth and so on until we get to yn, which is x to the n minus 1 e to the lambda x. All right. Proof. I'm going to use this thing called induction, if you don't mind. So if we look at, I'm just going to look at, so do you guys know how induction works? So suppose lemma 6 true for, 1, 2, all the way up to n minus 1, all right? I want to consider for n then. So I have d minus lambda to the n, and I need to look at x to the n minus 1 e to the lambda x. What happens? Well, that's d minus lambda to the n minus 1, right? And then I have the derivative of x to the n minus 1 e to the lambda x minus lambda x to the n minus 1 e to lambda x. All right, so what happens here? D minus lambda to the n minus 1, and then product rule gives me what? N minus 1, x to the n minus 2 e to the lambda x, plus lambda x to the n minus 1 e to the lambda x, minus lambda x to the n e to the lambda x. This calculation should be kind of familiar. These cancel, right? And we're left with this piece, right? But by the induction hypothesis, that's 0. I'm assuming that lemma 6 is true for like n minus 1. That would mean that if I have this acting on that, that's 0. Now, if you don't like this, that's okay. I get it. But we can keep doing this, right? I mean, you can look at d minus lambda cubed. A very similar calculation goes through the 4th, the 5th, and so forth and so on. Now, if you guys are awake and paying attention and like grumpy or just naturally argumentative, you might be like, but why are you multiplying by x and x squared and x cubed and so forth and so on? Let me show you why that's entirely natural. How about this? Is there a thing we can do without a lot of differential equations, which is kind of similar and will give us guidance? Like, what's the most basic differential equation, nth order, you could solve? How about this? D to the n y equal to 0. How would you solve that? Integrate one time, what do you get? We get d to the n minus 1 y equals to a constant, right? What happens when you integrate the next time? Integrate again. We get d to the n minus 2 times y equals to c1x plus c2, right? Let me put this in a different notation. So I'm saying d dx of y to the n minus 1 is equal to c1x plus c2. Now you guys will actually follow my next step. So I'd integrate both sides. The integral of the derivative is whatever's there, right? So I get c1 over 2 x squared plus c2x plus c3. I think I haven't gone far enough down yet. That should have been what? You guys should call me on this. What's this here? This should be what? Not n minus 1. I have d minus n minus 2 up here. It should be 3, right? And this continues. Eventually, you get y is equal to what? Is equal to cn plus, cn minus 1x plus cn minus 2 over 2 x squared plus plus, c1 over n factorial x to the n. Sorry, I can't do math. N minus 1 over n minus 1 factorial apparently is the pattern, yeah? What does that have to do with this? It's a special case, right? What happens when lambda equals to 0 in lemma 6? E to the what? 0x is equal to 1. So, and there's some, okay, fine, there's some constants, right? Fair enough. But this is like y1 equals to 1 is in here. You can see y2 is equal to x from this one. This is y3 equals to x squared, and so forth and so on. There's the yn, x to the n minus 1, because e to the, it's exactly this. But the things we're adding, the multipliers are a little bit different, right? Okay. So it's really not surprising, lemma. Lemma 6 is not as surprising as you might think it is, okay? Oh, yeah. Okay. Now, I guess beyond this, I just need a theorem. Here's the theorem. The general solution to, and I should give this thing a name. Let me call this thing up here L, all right, to L of y equals to 0 with L as above, right? Star. Okay, is as follows. Is given by y equals to c1y1 plus c2y2 plus plus cnyn, where L of y sub j is equal to 0 for j equals to 1, 2, n, and this set y1, y2, yn is linearly independent. Now, I don't want to make your brain explode, so I'm going to delay talking about what I mean by linearly independent for another day, okay? But, for example, these are linearly independent. So this is what we're after. This is the general solution. So basically what I'm saying is the general solution is going to be formed just like my nth derivative being equal to 0. It's a linear combination of these so-called fundamental solutions. These are fundamental solutions. All right. So what is this? I mean, what's the game plan here? To solve the differential equation we're after, what do we need to do? We need to find n linearly independent solutions. When we do that, we take an arbitrary linear combination of them, like that. Now boxed conveniently for you in a green. Now, part of the joy of coming to class is you actually get to see this, because if you're watching it later, you won't see it. Like this color is nearly invisible to the camera for some reason, but sorry, fun fact. So basically, we just, this is the recipe. All we need to do then is to find these fundamental solutions, right? How do we do it? Let me show you. So here we go. Example. Well, I was tempted to renumber. I'll keep. What example was I on? I'm sorry, I can't count. I didn't really. Example 4. I've only gotten 4 examples in so far. 3 examples? Goodness gracious. What's happened to the day? So this is example 4 then. Suppose you want to solve how about this? D to the 4th plus 4d squared plus 3, oh, that was a d cubed. Sorry about that. Plus 3d, that's a freedom I'm allowed, but you're not. 3d squared acting on y equals to 0. Now, AKA, this might have looked like, what it might have looked like in the textbook. Maybe it looked like y prime 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 plus 4 y prime 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 plus 3 y prime prime equal to 0. Okay? How do you solve that differential equation? Here's the way we do it. We say, aha, d to the 4th plus 4d cubed plus 3d squared, right, is equal to what? It's equal to d squared times d squared plus 4d plus 3, right? Which is equal to d squared times d plus 1 times d plus 3, right? So this is my L. This is the operator which defines the differential equation, right? I've now factored it. Okay? So my point to you would be if we take L, right, and we act on e to the minus 3x, right? That's d squared times d plus 1 times d plus 3 acting on e to the minus 3x, right? What happens when d plus 3 hits e to the minus 3x? Lemma 4. This is lemma 4 with lambda equal to minus 3. So that's 0. Right? Then we're feeding 0 into a composition of linear operators, which is a linear operator which sends 0 to 0. Or you can calculate it if you really must. Anyway, the point is 0. Right? On the other hand, we can look at L of e to the minus x, right? And that's d squared. And I can commute these factors. See, these factors commute. So I can make the d plus 1 hit the e to the minus x first because the operators commute. And that's super nice since the operators commute. Again, by lemma 4, this time with lambda equal to minus 1, what do we got? 0, so it gives us back 0. Right? By the same token, I can put the d squared, and I can let this act on x, or 1, right? I'll do x. So that's d plus 3 times d plus 1 times d squared. Let that act on x, right? What's the second derivative of x? 0, right? I'm really using lemma 6. Well, I'm sorry. I'm thinking of lemma 5 here. Lemma 5, y2 is x. So, again, what do we get? 0, right? And in fact, there's another one, which I won't write all the gory details down. I mean, I'll just write it down because I think I'm trying to make a point here. So L of 1 is also equal to 0, okay? So what do we got? Y equals to C1 e to the minus 3x plus C2 e to the minus x plus C3 x plus C4, that is the general solution to that fourth order differential equation. Does that seem too easy? It seems too easy, doesn't it? There must be some catch. No, these are that easy. Ooh. Whatever. I'm going to use it even though I erased it, though, if you don't mind. But anyway, I'm using it for specific. Now, I don't usually write down all these steps, but I wanted to illustrate the logic for you. The logic is that, example 5. So if I have something like d minus 2 squared times d plus 3 times d minus 1 cubed, y equal to 0, if I want to solve this thing. The point is, I can think about any one of these factors as going first. So I know that the thing that I just erased will be solutions for the whole thing. I mean, there's a theorem I'm using, right? The theorem is this. If L1 and L2, sorry, so if you have L1, L2, Lk of them, let's say, commute. If these are all commuting and are linear operators, let's say words, commuting linear operators, all right? Then if L sub j of y is equal to 0 for some, particular j, then if, I should say not then, I should say and if that, all right, then L, which is equal to L1, L2, Lk, also sends y to y to 0. In other words, L of y is equal to 0. And the proof of this, I just did like 3 times. I did it here, I did it here, I did it here. The proof is just that if this is L1, L2, Lj is somewhere in here, right? I can rewrite those as L1, L2, This is a hat you don't want to wear. Hat. So this means delete Lj from the list. Delete. So So if this is 0, right, then you feed it into here, the whole thing is 0. This is what I was doing. I commute it so that the thing that hits it first annihilates it. Then I feed 0 to the remaining operators, and I still get 0. But this is a general theorem. So let's just say that there's this theorem, and let's use it. Let's not keep going through this calculation every time. All right. So for this example, I'll show you how I actually write. You know what the work I usually show is? Here's what I usually do. This is the full solution. Thus, y is c1 e to the 2x plus c2 x e to the 2x plus c3 e to the minus 3x plus c4 e to the x plus c5 x e to the x plus c6 x squared e to the x, and there you go. The solution is already manifest if I have the operators factored in this way. I couldn't just do that for example 4, right, in its initial state, because the operator wasn't factored, right? But once I get to this step right here, once I got to that step, it was already clear to me what the solution was. Does this make sense? So what I'm using is that, of course, these two terms, right, killed by that, kill it, right? This term, that kills it. Kills this, I should say. These three right here, this guy, natural enemy of these, right? So this is the relation. And that theorem I wrote over there says I can think about them, whichever one first. And then the other theorem over here says, this is what I'm looking for. I'm looking for these n solutions. I add them together, take an arbitrary linear combination. That's the general solution. All right, let me go back to chapter 4 in your book. Y prime prime plus 6y prime plus 9y equals to 0. This is d squared plus 6d plus 9 acting on y equal to 0. Which is what? D plus 3 squared acting on y equal to 0. So by lemma 5 with lambda equal to what? Minus 3, right? In my current terminology. So I get what? Y equals to c1 e to the minus 3x plus c2 x e to the minus 3x. Hooray! Yeah, can I have another example? Sure, why not? I'm feeling magnanimous. Example 7. How about, here, I'll mix it up a little bit. Y prime prime plus y prime equals to 0, where y prime is dy dt. Uh-oh, it's a trap. Not a significant trap, though. So this is d squared plus d, right? Acting on y equals to 0, which I can say is really d times d plus 1, right? And that tells me then, paying attention to the fact the independent variable for this problem is t, so I'd write y is equal to c1 e to the 0, otherwise known as 1 plus c2 e to the minus t. There you go. General solution. Any questions?